Blast furnaces are generally aiming two gas flows, where operators aim for both a strong central and a strong peripheral gas flow to maximize productivity. However, this approach can often lead to unstable furnace operation. To understand why this instability occur and how to fix it, the researchers built a 1/15th scale cold model of 5800 meter cube blast furnace to simulate burden distribution and gas flow pattern inside the furnace. To ensure the model's finding uh, were applicable to real furnace, it was crucial to establish similarity condition. The team built a 180-degree segment model, which you can see in the, of course, later in the our presentation, complete with a rotating distributor and 2 year for compressed air. Three key similarity conditions were maintained. First, particle size distribution. The particle size for coke and ore were scaled down at ratio of 1 by 12 and 1 by 9 respectively, and the distribution was masked using the log normal distribution equation. Second, choose rotating speed. The speed was scaled to ensure that burden falling trajectory in the model were identical to actual furnace. And third, top gas velocity. The ratio of gas velocity to minimum fluidization velocity, or U over UMF, was kept the same. This ensures that gas solid interaction like particle fluidization are accurately replicated. The two gas flow charging pattern and its effect, so that the two gas flow charging pattern looks like inside the model. The key observation was the formation of a thin coke slit in the intermediate part of the furnace, roughly between 3/8 and 3/4 of the throat radius. This thin slit was made worse by several operational factors, as the gas flow, or what we earlier discussed, U by UMF ratio, was increased. The phenomena of coke collapse become more remarkable, further thinning the slit. The problem was also uh, increased by a higher ore by coke ratio and a deeper stock line. So, to these another parameter thin the layer thickness remarkably. Now, let's look closer at this collapse. The collapse occurs when impact of charging or physically pushes kick the coke layer towards the furnace center. The researchers quantify these using formation energy theory. The increase in central coke layer thickness, or delta LC, is directly related to the formation energy of the mix layer, which combine the collision and potential energy of the falling ore. Crucially, they found that decreasing the amount of coke charge to the center actually increased the slope of coke surface, and this gives falling ore more potential energy, leading to a larger collapse and thicker central coke column. Similarly, deeper stock line increase the ore collision energy, and also it resulting in a larger and larger collapse. Now, in this slide, the formation of this large central coke column is being discussed. How it create a new problem. Instability in the at the core. As ore layer are added, the gas flow becomes highly concentrated at the interface between central coke column and ore layer. The model showed that the largest fluctuation in gas velocity occur right at this interface. This finding was directly confirmed by analyzing throat gas temperature data from the operating blast furnace, which showed the biggest temperature swing at the exact same location. Furthermore, a small coke particles which are discharged last from the top bunker tend to land in center. This strong fluctuating central gas flow can easily fluidize this small particle, leading to central flooding, a phenomena observed in both the model and on the top camera of the actual furnace. Now, to quantify the problems of this thin intermediate coke slit, the researchers defined a factor called kappa K, which is the ratio of minimum coke thickness to average coke thickness. They confirmed that kappa value decreases, meaning slit gets thinner with an increase in ore by coke ratio, the gas flow, and the stock line depth. The consequences of this thin slit is severe. As the burden descends, this locally narrow coke layer reaches the cohesive zone where it restricts the smooth gas flow. This leads to significant gas flow fluctuation deep inside the furnace and result in unsmooth burden descending, which we observed as a slip. Having identified the root cause, the team used the model to find a solution. Through a series of optimization experiments, they determined that most effective strategy to solve this instability was to increase the proportion of coke charge to the intermediate part of the furnace. While reducing the ore in this area also helped, adjusting coke distribution had a much larger impact. The resulting optimized burden profile shown in the diagram successfully thickened the intermediate coke layer while still maintaining a strong concentrated center gas flow and moderate peripheral flow. So, in our this slide, in conclusion,